to solve the problem diameter of binary tree. Given a root of binary tree, return the length of the diameter of the tree. Diameter of the binary tree is the length of the longest path between any two nodes in a tree. This path may or may not pass through the root. The length of the path between two nodes is represented by the number of edges between them. Let's read this again. Given the root of a binary tree, return the length of that length from the length of the diameter of the tree. The diameter of the binary tree is the length of the longest path between any nodes. The diameter of the binary tree is the length, the longest path between any two nodes in the tree. The length of the path between two nodes is represented by the number of edges between them. The length of the path between two nodes is represented by the number of edges. So from the given example, let's go for the given example. 1, 1, 2, 3, 4, 5. So explanation 3 is the length of the path. 4, 2, 1, 3, 2, 1, 3, 5, 2, 1, 3. 1, 2, 3. So the number of is in the range of 1 to the power 4. The number of nodes. The root of the binary tree returns the diameter of the tree. So the left height and the right height of the height on tree. Diameter of a binary tree is the maximum number sum of the left height and the right height of one tree. Because the diameter of the binary tree is defined as the distance between any two nodes in the tree, the path may or may not pass through the root. But for any given node, the longest path that passes through it is a sum of the height of the left subtree. Left subtree is a sum of the height of the right subtree. So basically, it's the left subtree. And problem is something like this one. So let's simplify this problem. Okay, for null pointer, the diameter will be 0. Okay. For root node only, the diameter will be also 0, because here the diameter is the edge. First, you can see path. Okay. The length of path between two nodes is represented by the number of edges between them. Okay, so if there is only one root node, so there is no edge between any two nodes, so that will be 0. Okay? So for basic, let's say this tree, what will be its diameter? The diameter will be 1, 2. So if we add a null at the end of the every leaf node, what can we get? The sum, basically it is sum of length of right, sum of length of right subtree plus length of left subtree. So what is the length of this? Let's say it should be done 0, 0 and 1. This will be 0, 0, 1. The sum of length of right subtree plus left subtree. So sum of length of right subtree, the 1 plus 1, that will be 2. Okay, so 1 and 2. For root node, sum of length, the diameter of a binary tree is the maximum, and now the sum of the left height and the right height of the node in the tree. Because the diameter of the binary tree is defined as the longest path between any two nodes in the tree, the path may or may not pass through the root. For any given node, the longest path that passes through it is the sum of the height of its left subtree and the height of the right subtree. So for 2 only, height will be 1. This for 1. Let's take this example. Let's take this as an example. Null. Let's add. Okay. So this, for this, the sum of left subtree plus right subtree, that will be 0, 0, that will be 0. Okay, for this also 0, 0, 0. The sum of left subtree plus right subtree. For this, if this is 1, let's say 1, sum of left subtree plus right subtree, that for this it will be 0. For this, sum of left subtree, it will be 1 plus 1, that will be, for this again will be 1. For the sum of left subtree plus right subtree, that will be that will be 3. Okay, so root element plus its left subtree plus right subtree. No. If it's a leaf element here, it will be 1. Hope that if it's not a leaf element, it will be sum of its left subtree plus right subtree. Okay, if it's a leaf element, it will return 1. Okay. Otherwise it will be sum of its left subtree plus right subtree. So before, let's draw this one again. Let's try for so for this 1, 2, 3, 4. Okay, that's it. 1, 2, 3, 4, 5. 4 and 5. Okay, so for root, if both are null, it will return 1. Null, return once. Okay, now for this 0, if both are 0, left node, return once. If one, even one is not 0, then it will be 0, 1. This plus this will be 1. The height of its left subtree plus right subtree. So 1 plus 0 will be 1. Okay. For this 1, now this left subtree plus right subtree, that will be 2. This will be 0. So 0 plus that will be 2, but it's 1, 2, 3. 1, 2, 3. So if only 1 is null, this should also return 1. 1 plus 1, that will be 2. 2 plus 3. Then this should also return 1. 3 plus 2, that will be 4, but that is incorrect. So sum of height of its left subtree plus height of its right subtree, that is 0. Sum of 1, that is 1. Yeah. 1, 2, that is 2. That is right. 1 plus 1, that is 2. 1, 2, till this point. Okay. For this, the sum of height of left subtree, this should be 2, but it's 1 for some reason. It's returning 1. If this return 2, this will be 3. Then again, sum of its left subtree, that should also be 1, but it's 0. Let's go to the solution video again.
Hey everyone, welcome back and let's write some more neat code. So today let's solve diameter of binary tree. We're given the root of a binary tree and we want to return the length of the diameter of the tree, which is defined as being the longest path from a particular node. So in this case, it would basically be the longest path on the left side, which could either be this part or this part. Both of those are of length 2. I'm getting that calculation because 2 is the number of edges on that side for the longest path. On the right,
this will be 1. For this, it is 1. For this, it is 2. That is, this is determined. If it's left subtree, it is 1. It's sub. It will be 1. Oops. If it's written 1, then you just should. It's left subtree plus right subtree 1 plus 0. 1 plus 1 plus 1 left subtree. Is how can I get this is best for this 2. If this is 1, this is 1 plus 1, like this plus this. So this sum of its left subtree, that is 1 height. It's true. For this it's sum 1 plus 0. 0 will be 1 for this. Sum of 10 plus this is 1. It's 1. It's 2. Yes.
right side, we just have one edge, so that's 1. So the diameter through the root would be 2 plus 1, which is 3. But keep in mind that the longest path might not necessarily run through the root. So let's look at a counterexample. With this tree, if we try to calculate the diameter through the root, on the left side we have nothing, so that's a 0. On the right side we have 3. That's the longest path. You could take multiple different paths, but all of them are going to be of length 3, so the diameter from here is 3. But consider the node over here. Length on the left side is 2, and length on the right side is 2. So total is 4. That's the diameter of this tree. Now, I want to mention to you that this problem is actually closer to a medium problem than an easy problem. Why exactly is that? Because the solution initially seems pretty obvious, right? To get the result, we can just try to calculate the diameter through every single node in the tree. How do you do that? Well, just like I did, get the longest path on the left and the longest path on the right and add them together, aka sort of like the height on the left side and the height on the right side. Generally, we do this recursively with some kind of DFS algorithm, but the tricky part about this problem is that the return value, obviously, of this DFS is going to be the height. So what we want to return from this right subtree up to this node is, of course, the height. But that's not the result that we're ultimately trying to compute. What we're actually trying to compute is the diameter. Now, in terms of the code, there are multiple ways of handling that. The way I'll show you is sort of by using a member variable, or you can even think of it as sort of a global variable with respect to the recursive function. But the algorithm will be exactly like this. Recursively run DFS. From the left subtree, we reach null. So the height of that, of course, is going to be 0. That's what we return up here. Then do the same on the right side. And then we'd continuously go down. And so here we'd reach the case with just a node. The height of that we will say is going to be 1. That's going to be returned up to the parent. And that's basically saying that the length of this is 1. Same thing for this side. We'll say the length is 1. So now when we want to compute the diameter from here, we're going to maintain a global variable, which I'll call it the result, or this for short. And initially we'll set it to 0. This is what we're trying to maximize, of course. And from this node, we calculate a diameter of 1 plus 1, which of course is going to be 2 now. That's the biggest result that we have. Now, from this node, I want to return up to my parent the height of this tree. So what do I do? Well, the height is different than the diameter, so we actually will take the max of the left subtree, the max of the right subtree, and add 1 to it. Well, in this case, they're the same, so we just get 1 and then add 1 to it, which is this edge. So we'll say that the height here is going to be 2. Obviously, it didn't have of the right subtree and add 1. We actually will take the max of the left subtree, the max of the right subtree, and add 1 to it. Well, in this case, they're the same, so we just get 1 and then add 1 to it, which is this edge. So we'll say that the height here is going to be 2. Obviously, it didn't have to be like that. Suppose there was a node over here, and then maybe the height of this right tree would have been 2, and then we would have returned 2 plus 1, which would have been 3. So that's generally the core idea. We would do the same thing from here because it's kind of symmetrical to this side. So this would be 1 and 1. And then the height of this is 2, height of this is 2. Those are going to be returned up to 3, add them together, the diameter. So that's generally the core idea. We would do the same thing from here because it's kind of symmetrical to this side. So this would be 1 and 1. And then the height of this is 2, height of this is 2. Those are going to be returned up to 3, add them together. The diameter now would be 1 and 1, and then the height of this is 2, height of this is 2. Those are going to be returned up to 3, add them together. The diameter now is going to be 4. It's going to be increased all the way up to 4. From here, we want to take the max of left, max of right, it's 2, and we want to add 1 to it because of this edge here. So then we say the height of this part is 3. We return that up to the root. I'll make it another color, 3. Root is going to do the same thing. Take left plus right, add them together, we get 3. This time it's not greater than the result. So our result will stay unchanged, and of this 2, and we want to add diameter now is going to be 4. It's going to be increased all the way up to 4. From here, we want to take the max of left, max of right, it's 2, and we want to add 1 to it because of this edge here. So then we say the height of this part is 3. We return that up to the root. I'll make it another color, 3. Root is going to do the same thing. Take left plus right, add them together, we get 3. This time it's not greater than the result. So our result will stay unchanged, and it will be 4. 4 is ultimately what we would return. But it's not going to be returned from the recursive function. Keep that in mind. We're going to have we return that up to the root. I'll make it another color, 3. Root is going to do the same thing. Take left plus right, add them together, we get 3. This time it's not greater than the result. So our result will stay unchanged, and it will be 4. 4 is ultimately what we would return. But it's not going to be returned from the recursive function. Keep that in mind. We're going to have a separate variable that's sort of going to be global, which does that. And since we were able to accomplish this by just visiting each node once, we will say that the time complexity is linear, and the space complexity is going to be proportional to the height of the tree, which could be log n for a balanced tree or n for a non-balanced tree. So we're going to solve this recursive.
Yeah. Mm. There is two things. One is height, another is diameter. Okay, so both are two different things. Okay, so height. So what we do is, if we go to the leaf node, the leaf node will return 1. Okay, this will return 0. Okay, so for this node, the diameter will be 1 plus 0, that is 1. Okay, that result. So for right now, if we go to from DFS, we move from here, here, this will return 1, this will return 0. We do is 1 plus 0, that is 1. So our current result will be 1. Okay, result will be 1. So what we do is sum of left tree plus right tree, that is diameter. But what will this return? This will return the max. So max of left tree plus right tree plus 1. For this, what is the max? The max is 1. 1 plus 1, that will be 2. So this will return 2. Okay, again we'll move on to this right side of the tree. It will return 1. So for this node, the diameter will be 2 plus 1, that is 3, that is diameter. Okay, that is 3 is the diameter. So we check, is the diameter greater than the current result? As so remove this, we do 3. Okay, now what will this return? This will return the max of left or right subtree, that is 2 plus 1, that is 3. So this will return 3. Okay, we have a null node this side. Okay, null node. So for this node, what we do is we need to check the diameter for this node. The diameter for this node is left subtree plus right subtree. So the 0 plus 3, that is 3. Is the diameter greater than the current result diameter? No. So we just leave it as 3. Okay, so if so, that's the end of the problem from this node. Okay, but if there was another node here, let's say 6, this is the diameter. Okay, but what this node will return? This will return maximum of left subtree or right subtree, that is 3 plus 1, this will return 4. Okay, so basically the height and the diameter is the two different things. So for the diameter, what we do is left subtree plus right subtree. Okay, that will give us the diameter at any current node. Okay, any current node, we get diameter from left subtree plus right subtree. But what the current node will return is max of left subtree or right subtree plus 1. Okay, so that's the basic problem to get the diameter. Just remember, height is returned by the current node, okay, which is max of left right plus 1 and diameter of current node is the diameter of the current node is sum of its left subtree plus right subtree. Okay, let's implement this. Okay, let's try to implement this. So diameter of unbounded root is given. What we do is DFS. So we need to do it recursively. So if root equals null pointer and then 0 by simply. If root left equal null point and roots right equal null pointer, what it is, return 1. Okay, if both are null, this is 4. If the root one side, if left or right is 0, we return this. If root itself is null, we return 0. If root left and right both are null, we return 1. 2. Now we are doing this both because why we are doing both, because so why we are doing that, because if we have tree like something like this, if both is null, it will return 1. But what we do is we check its left subtree. Okay, we check its right subtree. Okay, so in that condition, if left is not null and right is null, or if for some case, let's say if left is null and right is not null, so there is 2. Okay, for any these cases like that, if one side is null and another is not null, for that cases we are returning 0, because what we are going to do is we are going to call this node left and right both. So left will go in and call its left and right, that will return 1. But when we are calling its left node, it will go and call this. But when we call its right node, it will be null. So for that case, we need to return 0. So that's the reason we are doing this and this. Okay, now let's move on. Okay, now what we need to do is we need to what now we have left and right. Okay. This again. If both is not null, what we're going to do is create an int. Let's say die. Okay. Die. Okay. That will be that will diameter of binary tree root left plus diameter of binary tree root right. So for the diameter, what we're doing is left tree plus right tree. Okay, simple. Sum of its left tree plus sum of its right. So instead of doing like this, what we do is let's do int left. Let's do this int right. The application. This the diameter is left, this is right. Now we have the current subtree left diameter plus right diameter, so we need to use result, that will be 0. Okay, so after getting the current subtree left current subtree diameter, what we will do is check if this diameter is greater than or equal to dash result. If it is, what we are going to do is it's equal to diameter. Now we go inside, check its left, check its right. If both return 0, if 1, that will return, come here. It will change this, it will come here. But what will it return? Return max of left right plus 1. So we need to return result here. The concept is simple. Like first, what we're doing is checking if any left or right is null, we'll return it 0. If both are null, we'll return 1. If left and right are not null, we'll take its left, take its right, and get the diameter at that current node. We add that, we get the diameter. We get the diameter, check if the current diameter is greater than the result. It is, we change it, then we move on. Now we need to return that current node should return what it should return. It should return its max of left or right plus 1 with which it is string. Okay, so this is correct. So but instead of doing this, we need to create another Okay. See, let's calculate an interior diameter. A function that will get tree node star root. Okay. What this is going to do? This is going to do all of this thing. Okay. Instead of calling, it will call calculate diameter. Okay, I will do all of this thing. Okay. Now this function will be called by this, that is root, and after getting called, after everything getting calculated, it will be done. Okay, result. Alright, okay. Let's make this. Okay, so what we did, it's working. Okay, let me explain once again how we how we did this solution. Okay. So basically, we are running a recursive algorithm. Let me copy all of this and put it here. Okay. It's the 60. Okay, that's fine. Let's move ahead. So what we are doing basically simply one second. What we are basically doing, we have created another function, okay, that will get us the result. Okay, and we are going to return that result. First, what we do is, now let's create 1, 2, 3, 4, and 5. Okay, let's add null nodes everywhere we need. Okay, so what we're doing is we're taking this root element and passing it to the calculate diameter function. So we check, yeah, if the root is null, so it's not null, it will go inside. Check its left is null, right is null, no it's not, so it will go inside. Now it will calculate its left, what you call, calculate left diameter, so it will go ahead. Okay, so it will go ahead again. This now this subtree from here, this point, from this point, from this point, it will into this subtree. Now this tree is passed in as a root. Again we check, is the root null, is its left null? No. Again we move on to this, it's left, again we move on up to here. We check is the current root node. We move on to this subtree. We check if the root is null. It's not null. We check it if it's left or right is null. It's neither left nor right. Okay, it's both left and right are null. So it return what it does. It return 1. Okay, we have 1 here. So we move on to this subtree. This is calculated. We want to write. So for this right, we check is the current node this is this. No, we move on to this set. It's left. Sorry, we went here, then this subtree. Now we move on to the right side. Is the this node null as, so this will return 0. So we for this subtree, left will return 1, right will return 0. Okay, so what we're doing is left plus right, that is 1 plus 0. Okay, that will be 1. We check is 1 greater than result. Currently result is 0, so as it is. So now result will be 1. Okay, now we check what this current node, that is this node, is going to return. So what this node is going to return? This node is going to return the max of left or right, so that is 1. 1 plus 1, that will be 2. So this will return 2. Okay, now we move on to this subtree. Okay, for this subtree, we have nothing here. Okay, null again. So what we do for this, check if it's check first if it is root. This node is null. No, it's not null. Check if it's left and right both are null. It's not null. Then what we do is we call its left root node, that will return 2. We call it right, that will return 0. 2 plus, then we have 2 plus 0, left as 2, right as 0. So 2 plus right, that is 2 plus 0, that will be 2. So check if 2 is greater than 1 as it is. So we remove 2, 1, we add 2. Then again, what this our current node is going to return, that will be 2, 0. The max is 2 plus 1, that will be, this will return 3. Okay, now we move on to the right. Do a few things. Okay, now we have the result as 2. This will return 3. We haven't calculated the right side. Now let's calculate the right side. So what we do, check for this node. We check is this node here, is this node this root node null? It's not null. Then we check if it's left or right is null. That is not true. Then what we do is calculate its left diameter, that will be 3. Calculate its right diameter, that will move the stack to here. So for this node, we come here, check if this node is null. So it's this condition is false. So we move on to this condition. Okay, so check if it's both left and right is null, as it's null, so it will return 1. So this will return 1. Now again we have calculated this and this. Now we'll move on to here. So we have 3 plus 1, that will be 3 plus 1, that will be 4. We check, is 4 greater than our current result as it is, so we swap it to swap with 4 here. Now again, what this node is going to return, so this node is going to return what you call 3 comma 4. What is the max? That is 3. So 3 plus 1, that will be 4. This will return 4 at end. This will return 4. This will return here we will get 4, but we don't need what the correct calculate diameter is. We don't need to return what the calculate diameter is giving us. We need to get the height. We calculate diameter is returning height. Just a height. We don't need height. We need diameter. Okay. So we already have calculated the diameter as a result. So we return result. Okay. If we are going to return whatever the calculate diameter is returning, that will be height of the tree. Okay, you can check 1 2 1 2 3 4. Okay, 4, we get 4. So we are so basically in this problem, simply if you think of this problem, we can think as diameter is left height plus right height. Okay, diameter of subtree. Okay, and height is equal to max of left height right height plus 1. Okay, simply just remember, diameter is left height plus right height, and height is max of left height or right height plus 1. So now let's move on to the next problem. Okay, okay. Let's go through the solution, like see the solution from his from NeetCode.
Hey everyone, welcome back, and let's write some more. Either of the subtree, get to actually call the recursive function here to update the same result that was declared out there. So this will do the same thing. So if we execute this, you'll see that once again it works. A local variable
is doing the same thing in, I think it's Python. Okay, so let's move on to the next problem of the tree. Okay, tree. Okay, balanced tree. So balanced tree, given a tree, determine if its height balanced. So this is the tree. Check if its height is balanced. This is a tree, returning true. For this it's returning false. Same, this it's 1 2, but it's for this side, its height is only 1. For this height balance, what does that mean? Okay, height balanced binary tree is a tree in which the depth of the two subtree of every node never differs by more than one. Okay. Okay, so all we need to do is what we did previously. Okay, we need to calculate the height of every subtree and check if its left and right is equal or just greater than one. If it's more than one, the difference from left subtree to right subtree is more than one, we return false, otherwise we return true. Okay, so let me copy this, paste it. Can I paste images here? Size, flip, remove background, rotate, edit. There is no distance. And now we have size. Resize. Okay. 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 So okay. So for this question, balanced binary tree, what we need to do is calculate the height at every point, every subtree. So for this, let's go away. So what if both are null? We previously in the last problem we calculated the height. All you need to do is if both are null, we return 1. And to calculate the height of this tree, what we do is take the maximum of both, that will be 1, and add 1, that will be 2. Okay, for this again what we do is if both are null, we return 1. To get the height of the current subtree, what we do is get the get the max of left subtree plus right subtree, that is 2 plus 1, and 2 plus 1, that will be 3. But at every point in the tree, like for every subtree, what we do is check if left minus right, that is 1 minus 1, if it's greater than 1, we return false, else we keep moving up in tree. Okay, till root. Okay, till root. So for this we can again check it's sub 2 minus 1, that is 2 minus 1, it is greater than 1. No, it's exactly 1, so we do nothing, we keep checking. Okay, so after we get 3, there is no left subtree with no right subtree, so we return true. Okay, so now let's erase this. Yeah, now let's move on, move this image here. Okay, for this problem again we do the same thing, calculate the height. Calculate the height of every subtree and check calculate the height at every subtree and check if left minus right is greater than 1. So for this it will be 1 1. The height will be max of left plus right plus 1, that will be 2. For this it will be 1, then max of left plus right plus 1, that will be 3. So while we check, we have for this left subtree, right subtree, so 1 minus 1, it is greater than 1, no, so we keep moving. Again 2 minus 1, the 2 minus 1, it is greater than 1, no, we keep moving. It will be 3, this will return 1, then 3 minus 1, it is greater than 1, s, so return false. Okay, all we do is calculate the height as a previous problem. Check left subtree minus right subtree, or right subtree minus left subtree absolute. This can be this also, like if for some case, for let's say that this tree is flipped, so this can be 3, right side can be false. So if we do 1 minus 3, that will not be greater than 1, but this should also return false. So what we do is get the absolute, so that this will be minus 2, absolute of minus 2 will be 2, which is greater than 1. Okay, for if the tree is, if this same tree is flipped, you cannot just do left minus right, otherwise sometimes we can get minus 1 or minus 2, which is still the false, but which is also false, but it will not give false if we just check this. So we do absolute of left minus right. So let's implement this problem. So what we do is basically simply check if root equal null pointer, then I will return 0. Check if root left equal null pointer and root right equal null pointer, and return 1. Else what we do is with left, that will be is balanced root left, and int right, that will be is balanced is right. Then we do is int diff, that will be abs of left minus right. Let's check if di difference is greater than 1, then we what we do is you return as false, else we return again as it's boolean. We need to create another function, so copy this, just name it int, check for balance BALAN, check for balance. Okay, tree node, okay, check for balance. If it is, what we do is paste if difference is greater than 1, we need to return bool. So what we do is we can do what we did in previous problem. We can create a global boolean variable and assign its true or false value here and return that according to that. Let's do that and then we'll try to simplify it. So it's bool, it's BLAN C balance. By default it will be true. Okay, so what we're going to do is return return true. Okay, this will come up with paste root what we don't care what this is going to return, because this is going to return the height. So what we do is BALANC balance is got false. Okay, otherwise what we do is max of left to right plus 1. Okay, let's send this run this one. Okay, so for true because we are not getting the false is balance. It's what it false if difference is greater than 1, which it is. We have left subtree plus right subtree, so we are doing is left minus right, getting the absolute value, checking that is if that is greater than 1, std open column C out di f. Okay, plus std C out. Okay. So 0 1 2, so we are getting 2. So when is 2 greater than 1, its balance should be false. Yes, sir. Is BALANC. That was a stupid mistake. We don't need to do any of this. Okay, so let's submit this. Which is fine, but what we can do is when we get false, what we want is stop the check for balance permanently and go ahead. So what can we do is so the problem solved. So basically what we did is what we did in previous problem, but even if we are getting like this difference, this is being false deep down inside the tree, we keep on calculating it till the what do you call till the till the root node. So what we can execute is if is balance is false, that is true. Yes, but it didn't return. Keep on returning 0. Okay, just stop calculating anything. Just return 0. Okay, so this worked. We stop calculating, going further into the everything will just return 0. It will be balanced. Okay, so let's put this into ChatGPT, see if we get more optimal solution, more simplified or optimal solution. So it's it. Your implementation is actually very close to correct and already efficient work, and you can use a form of height calculation. We are using form of height calculation with early stopping. That's the right idea. What would you avoid pre-competition or competition by combining height plus balance check? Okay. Your short circuit using is balance. Short circuit using is balance. Okay. Tempo is optimal of n, that is also fine. Mild issues was implement unnecessary leaf check. This part is redundant, and the recursion already handle this naturally. Really, that is students. Instead of global flag, we return -1. Global flag return -1 when the subtree is unbalanced. Okay, if left, check left. If left equal -1, return -1. Right, check root. Quality seems slightly screen due to the global flag and extra condition. Improved version, simple performance, more elegant and standard. No global. But this is a little more advanced or complicated. If I remove this line, we will check this left, that will not, it is null. Then go deep in. That it is going that checking the root. If it is null, so getting the root node, left, same left, and so on, and so on. Okay. So this problem works, so we don't need to complicate things. We are doing what we understand of it. So let's go to the solution. For this problem, okay. Tree. Check if the both three are the same tree. We can do simply by going from DFS and checking if the both the DFS is same or not. If the both value is same, then we like can be sure if both are equal.
Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve the problem balanced binary tree. We're given a binary tree and we want to determine if it is height balanced. What exactly do they mean by height balanced? Well, it's defined by saying that for every single node in the tree, if we take the left and right subtrees of this node, the heights of these left and right subtrees will differ by at most 1. So in here you can see, taking a look at the root node, it has a left subtree. What's the height of this left subtree? Let's call it 1, right? Because there's one node in the left subtree. What about the right subtree? What's the height of this right subtree? Well, it's 2, right? We can determine that just by looking at it. So then the left subtree has a height of 1, the right subtree has a height of 2. The difference is at most 1, right? Because if we take the absolute value of the difference, we get 1. So we'll say the difference is 1. So we just did that for the root node, but we have to do that for every single node to make sure that the left and right subtrees of every single node differ by at most 1. And just to show you a counter example, so this is kind of a badly drawn tree, but take a look at the root node, right? If we take a look at the left tree over here, the height is 3. If we take a look at the right subtree, the height is 3. So the difference is 0, which fits into our criteria. So from the root node, the left subtree and the right subtree are balanced. But if we take a look at, let's say, this node, right, we take a look at its left subtree, which is empty, right? So that has a height of 0. The right subtree has a height of 2. So in that case, the difference is 2 minus 0, which is 2, right? Positive 2, which is greater than 1. So just because from here, taking a look at the root node, the left and right subtrees are balanced, doesn't mean that that's going to be true for every single node, because we just looked at this node, the left and right subtrees were not balanced. How can we solve this efficiently? Let me first show you kind of a naive approach, and then we'll see how we can actually optimize that. So if we were asking naively, right, the first question we're asking is, from the root node, are the left and right subtrees balanced? How do we even determine that? Well, do you agree that we could probably do a recursive DFS on the left subtree to determine the height of the left subtree, do a recursive DFS on the right subtree to determine the height of this subtree, and then we could compare those and make sure that the difference is less than or equal to 1. Do you agree that we could do that? Probably, right? I'll explain more details in the code, but for now, let's just assume we can do that. We start from the root, we run a DFS on the left and on the right. That means we go through every single node in the tree, so we just did an O of n operation, right? And we were able to determine, okay, from the root node, yes, it is balanced, but we're not done yet, right? Now we have to continue to ask that question for every single node, right? So the next question we're going to ask is, suppose on the left subtree, right? From the left subtree, are the left and right subtrees from this node also balanced? And of course, they're both 0, so we determine that they are. And then we'll have to recursively go to the right subtree. From here, we're going to ask, are the left and right subtrees balanced? Yes, they are, but we'll recursively have to continue. We'll have to do that from this node, and then we'll have to do that from this node. Since we're running a recursive DFS on every single subtree on this root tree, we're going to have to do basically an O of n operation each time we ask that question. Is it balanced from here? Is it balanced from here? Is it balanced from here? And we could have a really big tree, and we'd have to do an O of n operation each time. O of n is the number of nodes in the tree, and if we have to do this n operation n times, we're going to get a time complexity of O of n squared. So now the question is, can we nodes in the tree? And if we have to do this n operation, n is the number of nodes in the tree, and if we have to do this n operation n times, we're going to get a time complexity of O of n squared. So now the question is, can we do better than that? Is there any repeated work? And I'll show you that yes, there is repeated work, and it basically can be eliminated by asking the question in a different order. What I mean by that is, instead of first asking if the entire tree is balanced from the root node, right? That's the first question we ask. Is it balanced starting from here? Instead of asking that, we do this bottom up. We recursively, instead of asking it from here, we're going to check, okay, is this entire right subtree balanced? Before we do that, we're going to ask, is this entire subtree balanced? And we're going to keep going lower and lower until we get to the base case. Once we get to the base case, then we're going to go back up, and I'll show you how that's actually going to end up eliminating the repeated work. If we do it in this order, we'll only have to visit each node at most one time, which will ensure the overall time complexity is going to be big O of n rather than n squared. Okay, so when we get to the root, before we check if it's balanced from here, we're going to check if it's balanced from this right subtree. That makes sense so far. And then before we ask from this position, we're going to ask, is it balanced from this leaf node, right? And now we can't really go any lower because this node doesn't actually have any children. So of course its subtrees are going to be balanced. But now we're good, right? We determine, okay, from this node, yes, the left and right subtrees are balanced, right? And then we pop back up suppose. And then we also want to make sure that this node is also balanced. It's the same thing, right? The left and right childs don't exist. So yeah, it's balanced from here as well. So we determined that, right? Now we know from at least these two nodes, yes, the left and right subtrees are balanced from these two nodes. Okay, now we want to know, is it balanced from this node? How can we determine that? Aren't we going to have to go back down and revisit the entire right subtree and the entire left subtree again? No, and I'll show you why. As we are determining if this subtree is balanced, let's also at the same time, simultaneously, let's make sure we get the height of this tree, the entire height of this subtree, and let's do the exact same thing for this node. Make sure we get the entire height of this subtree, because once we've done that, then once we go back up to the parent node from here, it will be easy. We already have the height of this tree. We already have the height of this tree. We can take the difference between those, make sure it's less than or equal to 1, and then we're good. We didn't even have to revisit these trees, right? From this node, now we've already determined, yes, it's also balanced from this position, right? So now we've determined it's balanced from this node, balanced from here, and balanced from here, and now we want to go back up to the root node and make sure it's balanced from here. Before we do that, we have to solve the subproblem on this left subtree. It's just a base case problem, right? It's just a single node, so we know it's balanced from here as well. So now we want to go back up to the root node. Is it balanced from this root node? Well, as we are doing this, right? As we were doing this right subtree, we determined the height of this tree was 1, the height of this tree was also 1, right? So now we want to know, before from this node over here, before we return back up to the parent, we want to know what's the entire height of this subtree. How can we easily determine that? Well, we know that this was 1, this was also 1. So from here, the height is just going to be 1, meaning this 1 comes from this node over here, plus the max of its left and right subtrees, which we know are both 1. So we can take the max of 1 and 1. That's going to end up being 1. So the height of the overall tree is just going to be 1 plus 1, which is 2, right? So the height of this tree is going to be 2. We determined that pretty easily, and that's what we can return back up to this parent node, which is good for us, right? And from this tree on the left, the height is 1 because it's just a single node. So we return that up to the parent as well. So now from here, we know that the height of the left subtree is 1, the height of the right subtree is 2. We can take that difference, 2 minus 1. It's 1, which is less than or equal to 1. So we do know that this is balanced from this node as well, right? And we can continue to recursively do that. If we had another parent node up above us somewhere, we could return, okay, the height of this overall tree is going to be 3, right? So that's the main logic we're going to follow. Yes, we're going to do this recursively, and there's many ways to code this up. The main way I'm going to code this up is actually by returning 2 values. I'm going to return a Boolean as the first value, which will be either true or false. Basically, for every single subtree, remember, we're going to determine, is that subtree balanced? We'll return a true or a false for that. And the second value will be the height of that subtree. So from this subtree, what we would return is true because it is balanced, and the height we would return is 2, right? The height of this subtree is 2, so this is kind of what we would return. Now, if we ever, from any single subtree, if we ever return false, that means we found at least one subtree that's not balanced. If we find even one subtree that's not balanced, that means from the root, we're going to end up having to return false, which I'll show you how we can implement that in the code. It's pretty straightforward. Okay, so now let's get into the code. And main thing is we're going to do this recursively. Why can't I just use this outer function to do it? Because this outer function just returns a single value, right? The Boolean, but we actually want to implement this by returning 2 values. So I'm going to write a nested recursive function here, and we're going to pass in a single parameter, which is the root. And remember, this function is going to return a pair of values, a Boolean and the height of the tree. So first things first, the base case. If the root is null, right? This means that we have an empty tree. So is an empty right subtrees were, but the balanced might not be. This balanced doesn't only mean is the tree balanced from the root position. This balance means is the entire tree balanced at all. Because remember, if the left subtree, for example, was not balanced, then this conditional is going to evaluate to false, right? Because this balance is only going to be true if the left subtree was balanced and the right subtree was balanced. And
we are getting this picture. When we go to the leaf node left will be 0, leaf node right will also be left node right also be 0. So we'll get 0 0. It calculate up to here. We'll get 0 plus 0, that will be 1. Okay. So we do not need to do that one. This previous problem. Let's the diameter problem. check if both. So we can remove this again. Don't need to do that because we are already doing 0 plus 0 plus 1. So that is one. Okay. What we are doing is for the leaf node, we are getting 0, 0 plus 1, so we are getting the height of 1. So for the leaf node, we get 0, 0, 0 plus 0, that will be 0. So 0 is greater than 0 node. So while returning, we return 1. Okay. So let's see this problem. Same tree. Given the root of two binary tree, P and Q, write a function to check if they are same or not. The two binary tree are considered the same if they are structurally identical and the node have the same value. Okay, given the same value and identical, okay. Structurally identical and same value use. So 1, 2, 3, 1, 2, 3, true. 1, 2, 1, not 2. So this one false. 1, 2, 1, 1, 1, 2. So this one false. So for this problem is same. Same as the before. All we need to do is go according to DFS. Okay. What we can do is check if the both of the string are same. Okay. We can do BFS or DFS, any of that, and while we can at simultaneously we'll go through both of this tree, check if both the node are same. You know, both binary tree are considered the same if they are structurally identical, and the node have the same values. Okay, structurally identical values are the same. Left is null. So what we can do is we can create a true vectors that will store the BFS and DFS of the nodes. And after storing the both BFS and DFS value, we can compare both. Let's do this. Just get two stacks, add the element to the check if both are the same. Stack of 3 nodes. Stack of 3 nodes. Q stack, okay. P stack and Q stack. While PS stack empty or empty is not empty, and QS stack is also QS stack is also not. Both are not empty. What we will do is let's just add PS dot P use okay. QS dot push Q. Okay, push both of them. Check if both are not null. Then what it is, check if PS, a PS dot PS dot well equal PS. We just don't need to check one. Okay, for this we'll get one. Okay, that will not be a problem. We're checking if both of the value are same, but if we're checking one, then one push its left also. If it is null, what we do is for this left and right in this tab, what we do is when any of the value is null, if not null, we are pushing. But in this condition, we will check. Okay, let's first let's do this here. QS top valve, check if those valves are same. Both valves are same. If they are not equal, then all we need to do is on the term. So now we need to do what we need to do is instead of doing it like this, let's create a temporary node. Node start ET. Let's go to this one. Tree node QT temporary. Let's get them. Stop. Well, then pop both of these values. Okay. Yes, dot pop. Okay. Yes, dot pop. Check. Let's add. We are adding. If not null, if select is not null and QS left is also not null. Pointed and it's not null point. Then this is the push yes, T left and T left. This is that push t is t is the push qt left. Both are not null. Else if any of these if both are not null, then push back. If any one of these, one is true, another is false. If one is false, false, also false. So both are null. Don't push anything. If both are not null, push. Both are, one is null, another is not null. If both are null, check. Photo blind. Just right. There's one simple way, like we can go through both of this tree, get the DFS and compare it, but I'm trying to do it one go. So here's the push back left, right, right. So left, right. If both are not null, push. Like, but in this condition, one is pushed. Okay. Now if one is pushed, then it will go two. So this is the same. It's not a null pointer. This will say it's a null pointer, so it will not push anything. It will come here. It will go left again, push anything. So that will be problem. If one is a null pointer and another is not a null pointer, both are not a null pointer. It's not equal to null pointer. That's it. If both are same, this side, both are null pointer. It's not. Same thing. But in this condition, this is it's left. It's not a null pointer, but this left is a null pointer. So we do not push any of this. We are not pushing any of this. See the value, the value can be in this case, okay. 10 to the power 4 positive and 10 to the power 4 negative. So both for this condition, this is not we're trying to push null. This condition will feel like this is 1, okay? So it's not a null pointer, okay? But this will give it's a null pointer, so neither this will not this will be pushed. We'll move on here again. So at the end, if we this condition will not be none of this will be pushed. Will at the end done and true. So either even if this is false, it will get true. Instead of doing this, but if we push null pointers, it will go ahead. It will keep on like it will go ahead null pointer again null pointers. Two binary trees are considered the same if they are structurally identical and the node have the same weight. If both node are not the same, given the two binary tree P and Q, write a function to check if they are same or not. Okay, it's not just left. These two are not the same. Okay, these two are two different trees. Structurally identical. Okay. Let's check what is the 10 to the power 4 population. 10 to the power 10 to the power 4. What is how much is that? 10 to the power 4, that is only 1000. Okay, so it can only be up to this up to 10,000. So instead of doing this, and my node is only 100. Okay, so we can do one using vectors. Just whenever there is a null, we push instead of value, push int max or int min and check. If do not null, it is it is not null. If else we push by percentage true. Create a vector. Vector of int p val vector of int q val. Okay, so table. Need to push this value and this value. So the p val push back p q val dot back q val. Okay, so what it is, if it is not null, what it is, val dot oops, back val. Else if it is null, what it is, this instead of pushing this, what it is. What I'm trying to do is create this structure using these vectors. Okay? So what I'm trying to do is int. It's okay. Let's do the same thing. Q dot val. We have to push back to left. Okay, it's it is back to int. That's something over here. So this paste it here instead of left. Let's do exist. It's st. So I will have to this paste it here. Okay. Else with similar as ever at the end of this cycle. If you return this, compilation period use terminal. So these are the functions. So ps dot top and dot sometime that ps top. Okay, pdf valve. Extra semicolon. Semicolon. Both are not null, then we are pushing. If it's null, what we're doing is it can be accessed with a null pointer of it's out. What we will do is check and I will 0. Wow. What's going to and curious null pointer, what it is 10 beyond 10. So both are null. Because both are the same there. Okay. Null pointer and it's not equal to pointer, then return out false, same thing. B is and it's not equal to false. So the 0 is less than value size specific. We're going to check this value. So it is not equal to size again. Return false. actually. Returning false if both are not of the same size. If both are of the same size, all we want to do is check if p val I equal q val I. If it is not equal, so all we want to do is return return false. Let's see. That point is not now. And this coming out this line, these lines. If it is not, okay, if it is there, if these are there, all we need to do is before hopping, well, this line, well, push back, PT, okay. We can do so much to do that right now. We will push back, PT, this slide. Certain this condition one. What it is, pushed one, then for second iteration when you come, isn't it? We have pushed maximum, then we have pushed see out. So this true. Is that I it's not enough. this problem, what is happening? Put one, we're pushing, push one, that's fine. And we'll check its left. Check this it left, that is not null, so already we pushed it. This is not going to run. So for this particular, this null, so pushed this, and for this, check this, it's pretty right. This is null, so push this. Okay, but at the end we're getting the same amount. Because on the left and right is shading. So this is not working because we are like what is happening? One, this is getting pushed. When we come check its left, we are pushing this. One getting pushed in second iteration. When we check its left, which is 2, so 2 is not getting pushed, which we need to push here. It's not getting pushed here. And then we go ahead, we push this one. But we are pushing this, it's left. Okay, that's the issue. Need to comment on this. These. This should work, but it's not working for some reason. Let's put this in both sides together. Your data service and really bad implementation with a few useless really work, but it is so much complicated than needed. Let's go through it clearly. If both are wrong, it's pretty left. Well, so left, pretty left, well, it's the wrong push. So this should be this left and 20. QT. We're getting error 4. Okay. One is empty, another is not empty. If this is equal to P is equal to P is not a null pointer, but Q is a null pointer. It should return false. If both are null pointer, this should return true. There is 2. If P is an null pointer and Q is not a null pointer, P is not a null pointer, Q equally has null pointer, return false. Still is problem. Okay, pair both. Efficiency and parametric internal file. Push here and here, we must compare the internal files. I did that previously. See this, I did that previously, but I removed it because of this. This. Put it here. It's return true, this is return false. Both are null pointer, right? Both are. But P is not a null pointer, but Q is a null pointer. It's a return false. It does not return false for some reason. If both are null pointer, return false. If any of those is not pointer, return false. If any is equal not pointer, return false. If any of this is not pointer, return false. Okay. It works right now, but it's not working still. Not working. Some For some reason this solution is not working, so let's go through the tedious solution for this problem. Okay.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve same tree. So I'm going to upload this on a Friday. So today we're going to be doing an easy-ish problem. So we're given the root of two binary trees, P and Q. We need to write a function to check if they are the exact same tree or not. We can determine that by one, making sure that the structure is the exact same. So for example, basically the number of nodes, right? Like they both have a
See, let's try to understand this. What I'm trying to do is try to do the papers. E, and pointer with return. Hello. Either this one. Hello. P value now what we will do is instead of like we check for this, now we are going to check for this and this. So what we're going to do is 68. What we're going to do is these so now we check like first it will come 1 1. So is this true false? No, this true is both equal as. So what we will do is return true. So return true. So this will not happen right now. It should happen after. So return false. Not equal to. So those these are not equal. So if this is not equal to this, return false. But first, if both are same. Oh. So what we are doing is checking if both are null, return true. Checking if either of these is null, and we return false. Okay. If like first one is, this is null, but this is not null, so we return false. Now what we check? Now check if both of these values are not same. If it is if it is same, then we return true. But if we return true in first iteration, if we return true in first iteration, we'll never know if any of the inside of this will be false. So if these two are not equal, then we return false. If those two are same, what we do is we move inside the tree. What we do is send P left and Q left. Okay. And now check if this and this is same. If both, if this and this is same and is same tree, the right. tree. Yeah. Easiest way to like first what do you think? Checking if both are null. No, it's not. Check either of it is not. No. So checking if one is not equal to one, but it is equal to one. So we move on. So we come here. So we check if two, then we send here 2 and 2 again from top down. Check if both are no. It check if 2 is not equal to 2, it is equal to. So we move on. We go to the right side. We check if 3 is not equal to 3. So we move on. So we go ahead. So now from here we get its left and its left, which will be false, which we will get here false. So this will be false, but this will be true. This will be false again. This will also be false. What it is, check this inside here if it is null. Inside here it is null. So both are null, so return true. This will be true. Then check if it is inside there is null. Null, so this will also return true. So both of these will be true. This will be true. Solution once again.
A root node, they both have a left child and they both have a right child, right? The structure is the same. Not only that, though, they also have to have the exact same values at every node position. So in this case, we can see they have the same value. Once again, same value in the left side, and
Recursively, no? Recursive. Yes. Bring it recursive. Breadth for search. This is recursive breadth for search with this. If it's only one, check if it is true. If it is not, if it is breadth for search.
lastly, same value on the right side. So these are the exact same tree, right? So we can return true. Now, if I got rid of one of these nodes, right? Let's say I just got rid of this, then it's definitely not the same tree, right? Or if I took this value and changed it, let's say to a 10 or whatever, then it's also not the same tree because the values in this case are different, right? The main thing to notice with this problem is it lends itself very well to recursion, and we know that there's a pretty convenient recursive way to traverse trees, and that's depth first search. We're going to be using that recursive function to solve this problem. So remember, we're trying to check if these are the same tree, right? So that's a big problem. We're comparing the big trees. Can we break that down recursively? Well, first thing to intuitively check is we really just need to check the root nodes, right? Are these the same? That's the first thing to check. Are the root nodes the same? If they are, we're going to continue the function. Now, if they were different, for example, maybe this had a different value if it was true, we immediately return false, right? If even a single node doesn't match, we can return false. Nothing more is needed. Now, if they do match, right, these are equal, great. Now, this is the recursive part. We don't have to consider this node anymore, and we don't have to consider this node anymore. And now we have changed the problem. Now we actually have two trees left. We have one left subtree, right? These are the left subtrees. And we also have two right subtrees. So this is the right subtree of the first tree, and this is the second right subtree. So now the problem is changed. Now we're checking, are these two trees the exact same? And are these two trees the exact same, right? So we've changed the problem. It becomes recursive, right? We're now going to be looking at the subtrees, comparing them. Now, both of the subtrees need to be equal, right? These two need to be equal, and these two need to be equal, and then we can return true. And we're just going to continue to break this down. Obviously, the tree could be much larger than this, in which case we would continue to do that. Now, let's not consider this example anymore. We know with recursive functions, the main thing to consider is the base case. So what are a couple base cases? Well, what if we had two null nodes, right? They're both empty. What are we going to return then? Is this the same tree or is this not the same tree? Well, they're both empty, right? So that's technically the same tree. In this base case, we return true. What if the left tree is null, but maybe the right tree has a single node in it? Now, this is obviously going to be false, right? These are not the same tree. And the exact same thing could be true. We could have a null in the right tree and a real node in the left tree, and that would also be false. Now, the case where both nodes are non-null, then we're going to be looking at the values. Obviously, if the values are the same, that's true, right? That we're going to be returning true. They're the same tree. If the values are different, we're going to be returning false. So these are basically all of the base cases that I went over, and the code is just basically going to be implementing exactly what we just showed right now. So let's jump into that. Oh, and last but not least, the time complexity of this. So the time complexity is overall going to be basically the size of both trees added together. So the size of p plus q, because worst case, we would have to iterate through every single node in both trees. So that's basically the overall time complexity. So like I said, this is going to be a recursive function. Since we already went through most of the base cases, this is going to be pretty easy peasy. So if you know depth first search already, we know the base case is important. So if the first
So this is it for now. We'll come back. We'll come back and try to solve more problem in next session. Okay. So